Hi everyone, welcome to our webinar today. Our topic for this webinar is severe weather and the reliability of the U.S. electric power grid. And this webinar is a presentation of Clean Energy Group's Resilient Power Project. And as our host today, we have Seth Mullendore. Seth is a project manager for the Resilient Power Project here at Clean Energy Group. And before I pass things over to Seth, I would like to go over just a few quick housekeeping notes with everyone. All of our participants today are in listen-only mode. That means that you can hear us, hopefully, but we cannot hear you. You have a couple of options for joining the audio portion of this webinar. You can use your computer, mic, and speakers, or you can call in using your telephone. We have some instructions on the screen there for you for the audio options. And we also ask, very important, that you submit your questions throughout the webinar as you think of them, and you can do that by typing them into the webinar console and hitting send in the question box there. It's important that you type them in as you think about them and don't wait until the end. We will be having a Q&A following our presentation today with the audience, and we will be reading through your questions as you type them in. So please get your questions in so that we have a better chance of answering them. And a final important note, this webinar is being recorded. You'll find a recording of this webinar as well as slides from the presentations on our website at the two web addresses that you see on your screen. With that, I will pass it over to Seth Mullendore. Seth?
Thank you, Sam. So thanks for joining us, everyone. As Sam mentioned, this is a presentation of the Resilient Power Project, which is a project run by Clean Energy Group. Clean Energy Group is a national nonprofit that works to advance clean energy technologies and markets and financing opportunities for clean energy technologies. The Clean Energy States Alliance is also a sister organization underneath the Clean Energy Group, which is a group of clean energy administrators from our states around the country that are involved in clean energy programs and funds to support clean energy technologies at the state level. The Resilient Power Project is the Clean Energy Group in conjunction with the Meridian Institute. It is generously funded by the JPB Foundation, the Kresge Foundation, and Surdna Foundation. It's been running for about a year and a half now, and was started in the wake of Hurricane Sandy and other disasters that have affected the East Coast. So if we can go to the next slide here. Just to let you know a little bit more about the Resilient Power Project. It's not just in the East Coast. It is actually a national project to provide a more resilient solution to power outages across the U.S. In Hurricane Sandy, which occurred just about 3 years ago now. A lot of residents, 8 million residents, were left without power, and the typical backup generators that are used to support people in those situations often failed. So we're looking at cleaner and more resilient solutions to that. The solution that we've looked at the most is solar energy, usually solar PV, combined with battery storage technologies that are able to island themselves from the grid when there's a power outage and continue to power critical loads for those in need. So through the Resilient Power Project, we're trying to increase awareness about these clean solutions for resilient power. And we engage a lot of city officials and state officials to help them develop their resilient power policies, help prepare for the next major outage, and work on programs to support these technologies. In particular, we're looking at protecting low-income and other vulnerable residents, such as the disabled, those in senior communities, and in affordable housing, as well as the facilities that support those communities, such as emergency shelters, fire stations, police stations, and things of that like. So we advocate for policies to help improve resiliency at the community level. We do this both at the state and federal level. And also for developers and communities that are looking to become more resilient and are looking to adopt clean energy solutions to provide power in emergencies, we do have a small technical assistance fund that can help pay for the pre-development costs, the scoping and feasibility studies of projects that are looking to get started and provide more resiliency for their residents. So our website's up here, resilient-power.org. You can see we have a number of reports. There are a few of them listed there. We also have monthly newsletters as well as weekly updates on some of the technologies and recordings of our webinars, including the one today will be up shortly. So if we can go on to the next slide. I wanted to let you know about the newest report that we've done here at the Resilient Power Project called Resilience for Free. This report just came out today, and basically it's looking at solar and storage technology solutions in 3 major cities in Chicago, New York, and Washington, D.C. for multifamily affordable housing buildings. And it's an analysis based on real-world economics, what these projects then actually cost, and the revenue and savings opportunities through providing grid services or cutting down on utility demand charges. And found that over the lifetime of these projects that they actually had a positive payback and had a simple payback that was less than the lifetime of the project, as low as 3.5 years in the case of Washington, D.C. under certain circumstances. So there's a link for that webinar there, or for that report there. We are going to be having a webinar on that on October 29th. The webinar today is the first in a series of 3 that we're doing to mark the 3-year anniversary of Hurricane Sandy, which occurred at the end of October 3 years ago. So if we can go to the next slide. I'd like to introduce our guest speaker, Pete Larson. He's going to be presenting the findings from a report that he was lead author on called Assessing Changes in the Reliability of the U.S. Electric Power System. Pete is a research scientist and assistant group leader in the Electricity Markets and Policy Group at the Lawrence Berkeley National Laboratory. He conducts research and analysis on electric reliability, energy efficiency, and regional electric system planning. He has previously worked at the Institute of Social and Economic Research in Anchorage, Alaska, and the Societal Impacts Program at the National Center for Atmospheric Research, as well as Stratus Consulting. And he has taught at the university level at the University of Montana, Cornell University, University of Alaska, and the University of California, Berkeley. Peter has an MS degree from Stanford University in Management of Science and Engineering, as well as Cornell University in Natural Resource Economics, and a BA in Economics from the University of Montana in Missoula. And Pete is currently a PhD candidate at Stanford University. So with that, I'd like to remind people to please enter questions as they come along to your mind, and we'll address those at the end. With any time that we have remaining, and I'd like to turn it over to Pete.
Thanks, Seth and Sam, and the rest of the Clean Energy Group for inviting me to speak today. Again, as Seth mentioned, I'm going to be talking today about severe weather and the reliability of the U.S. power grid. I wanted to point out this picture that was taken here from my local newspaper. This was a power outage caused a couple miles from my house on Sunday, and so we're seeing these sorts of impacts all over, and this one just happened to be very close to my home. So advance the next slide, please. So this report came out about a little over 5 or 6 weeks ago. This was a project that we worked on at LBNL in Stanford for about 1.5 years, maybe a little bit more. It's the second in a series of major papers we've released on the reliability of the U.S. power system. And I would be remiss without mentioning who sponsored this work. I like to do this up front. The Office of Electricity, National Electricity Delivery Division, NED, funded this work. So the agenda for today, I'm planning on speaking for about half an hour, so we have plenty of time for questions. We'll talk a little bit about the background on the project and some of the questions that we wanted to answer. I'll spend a little bit of time talking about causes of power outages and how reliability is typically measured by distribution utilities. Talk about how we got data for this project. I'm going to spend very little time on some of the more sophisticated econometrics because I don't think it's relevant for this audience, but if you have questions about that, we can talk more offline. And then I'm going to get into the findings, and I'll talk a little bit about the caveats that should be thought about when interpreting, the results from this model. And finally, I'll conclude. So my colleague Joe Edo and I and a number of others released a report back in 2012 where we looked at reliability information from over 150 U.S. electric utilities from 2000 to 2009, so about 10 years. And at the time, we accounted for about 50% of total electricity sales in that data set. And what we found in that report, which was published in Energy Policy, is that the duration and frequency of power outages was increasing by about 2% per year over that 10-year time frame. A key component of that report is really we acknowledged that a lot of additional research needed to happen in order to fully explore the issue of reliability of power systems. So we identified some areas which we thought would be fruitful areas of research. The first is it was clear that we needed to come up with more disaggregated measures of weather. In the original study, all we really had was heating degree days and cooling degree days, and I think basic precipitation information. It was very basic model of weather in this model. The other thing we identified as a future area of research was what are utility characteristics that might influence reliability? So population density, the number of customers that are rural versus urban, the extent to which the system is undergrounded. We've heard of places in the U.S. like Washington, D.C. that are in the process of going 100% underground on their distribution system. And finally, how is utility spending related to reliability? So the key questions we wanted to ask were, for this new study, are warmer, cooler, wetter, drier. All of these differences against an average year, how are they correlated with measurable changes in the duration or frequency of power interruptions? Second, are the number of customers or sales or underground line miles or the presence of what we call outage management systems? These are computerized systems used by distribution utilities to respond to outages. How would the installation of these systems be related to reliability? And finally, we were really curious if there was a nonlinear relationship for the folks that are, not savvy on some of the math. The idea is that, weather, whether it's wind speed or whatever the measure of weather is, has kind of a nonlinear effect on reliability, meaning if wind speeds go higher and higher and higher, the impact isn't constant, it changes, it increases or decreases as the wind speed or whatever metric we're looking at increases. And then finally, our previous year expenditures correlated with reliability, and whether the key question we're really most interested in understanding is, are there trends in reliability? Are the power outages, the interruptions, lasting longer? Are they becoming more frequent over time? So this is these two pie charts are a subsample of some utilities that we were studying. And a lot of these answers shouldn't surprise anyone. What are the causes of the increase in the duration of reliability events? What we did to create this graphic is we reviewed reliability reports from a handful of utilities and tried to organize them by common responses. It's very difficult because everybody reports the cause of an outage differently, but we tried our best to sort of bin these into common categories. And so on the duration side, you see that, failures in transmission and distribution equipment account for about a quarter of, the increase in the duration of reliability events. Planned outages, 10%, vegetation, this is trees, overgrowing and touching the line, causing an arc. That's roughly 21%. On the other side, what causes an increase in the frequency of reliability events? You see the breakout. It's somewhat similar. The interesting finding to me, and again, this is a subsample, so I wouldn't read too much into this, but is that wildlife, this is squirrels and birds, and we've also heard of cases of rats causing power interruptions. It turns out that 11% of the frequency is caused by wildlife, but the duration is much shorter. So you could infer from this small sample that, wildlife cause power outages, but they're quick to be responded to by the utility. They're able to correct or address the interruption fairly quickly if, a squirrel causes a reliability event. So there's 3 or 4 common reliability metrics. We focused on 2 of them for this report, SAIDI and SAIFI. SAIDI, for those not familiar, is called the System Average Interruption Duration Index. And basically all you do is you take the amount of time that customers are without power and multiply it by the number of customers affected by that outage or interruption, and you divide it by the total number of customers in the utility for every year. So it's a measure of duration, how long an interruption. It's essentially the total minutes that the average customer is without power in a given year. System average interruption frequency is pretty self-explanatory. It's really how many times is the average utility customer without power every year. And these are the 2 metrics we focused on in our 2012 paper, and there's the 2 metrics we focus on in this paper. So these graphics, there's no fancy econometrics here. This is the raw data before we do any of the economics hocus pocus. And these are really interesting graphics. The gray area, the area is really the bottom line, or the bottom of the gray area is the 25th percentile, and the top of the gray area is the 75th percentile. So what you can say is this whole gray area is the middle 50%. These aren't the extremes. So if you look at SAIFI, which is just the count of interruptions for an average customer across the U.S., what you find is when you don't incorporate what we call major events, SAIFI is fairly flat, roughly 1.2, 1.3 outages for an average customer across the U.S. If you look at the graph on the right, this is if you include what utilities define as major events, and these are typically severe storms. These are the Hurricane Sandys. These are the Hurricane Katrinas. These are, very significant tornado events. If the utilities incorporate those major events in their reliability, you can see that SAIFI increases. There are more interruptions for an average customer, and you can see a little bit of an upward trend, and this is just the raw data. On the duration side, one second while we advance the slide here. On the duration side, without major events, SAIDI is roughly about 2 hours. The median across the U.S. in our sample is about 120 minutes when you don't include these major events. However, when you do include the major events, things get really interesting. In the early 2000s, we're showing the median SAIDI value at roughly 2 hours, but towards the latter part of the decade into the next decade, so this is the 2010 to 2012 period, you see that SAIDI has increased pretty significantly. And again, this gray area is just the middle 50%. You see a big spike in 2008. There are plenty of utilities above this gray bar because this is just the middle 50%. One very important thing to mention here, and this is a really key sort of policy issue related to reliability. The criteria used to classify major events typically varies by utility or public utility commission. And so there's not a consistent definition being used across the U.S. about what constitutes a major event for a specific utility and whether utilities should include those major events in their reliability reporting. So a little bit about the data we collected. As I mentioned earlier, the Edo et al. Study, which I was part of, we got 155 utilities back in the 2012 paper. We're now approaching 200 utilities, representing about 70% of the U.S. in sales. We got this reliability information, the SAIDI and SAIFI, from discussions with Public Utility Commission staff, with Public Utility Commission reports, with utility press releases, and utility reliability reports, among other sources. I'm listing, I won't go through all of these. The one I will mention is lightning data. We were really interested in seeing the effect of lightning because lightning is a good proxy for severe storms. And it turns out that there's a data set called the National Lightning Detection Network, and we were able to get that data and map it to all of the utilities for the years of the analysis. And so that was a major accomplishment. We were able to get weather information and information about transmission and distribution lines and expenditures from either FERC or through Ventex, which is a subscription service to provide data on utilities. So there's a lot of numbers here, and I'm not going to go through them in much detail, but I will show you that, as I mentioned earlier, without major events, the average SAIDI, the average total minutes an average customer is without power when major events are not considered is a little over 2 hours, or in here in this table it says 125.6 minutes. If you look down the same metric, the median with major events for SAIDI is 173 minutes. So right there you're seeing almost a 50% increase just in the medians in SAIDI between the without and with. And that's a major theme in this report that we'll talk about a little bit later. So one of the questions we had in the original 2012 study, and we wanted to ask again for this study, is how representative are those 70%, are those 200 utilities representing 70% of sales? Is this a representative sample of the U.S.? Well, if you look at size of utilities, on the left pie chart, that's what we have in this study. Roughly 17% of the large utilities are covered in our study. Nationally, about 14% of utilities are what we consider large utilities or greater than 1 million customers. So if you just compare these pie charts, blur your eyes, just look at the shapes and the colors, you can see, hey, by size, this study is quite representative of the U.S. when you measure it by size of utility. Another story emerges when you look at ownership, and this is a very important caveat. Ownership, there are a number of different ownership types in the U.S. for utilities. There are investor-owned utilities, which many people know as IOUs. There are cooperatives, and then there are municipally owned or government-owned utilities, and then there's sort of another category. When we look at this study and we compare it to the total U.S., what we see is we have an overrepresentation of IOUs in our panel data compared to the U.S. and an underrepresentation of the number of cooperatives and municipally owned utilities. So that's a key thing to remember. The challenge here is that it's very difficult to get reliability information from co-ops and from municipally owned utilities. PUCs have the ability to require IOUs to file reliability reports. But right now, we don't have a good amount of time series data for co-ops and municipalities. So the next few slides are going to be some maps of the data. We really like maps, and so they're kind of interesting. I'm showing them here to give you an idea of the coverage, the geographic coverage, but also just to show that, the information in these maps is consistent. We don't want to see places with huge precipitation levels in the desert Southwest. And so by mapping this, it looks really nice, but it also just tells us whether the data makes sense. Heating degree days, for those who aren't familiar, heating degree days are a measure of cold temperatures. These are days when you typically turn on your furnace. And so places in the North Plains, the Montanas, the Wyomings, and the New England, of course, have the most heating degree days. typically the coldest climates. On the cooling degree days, these are places that are typically warmer. These are days when you want to cool your building or your home. And so not surprisingly, the south, if you look down Louisiana, Texas, Arizona, these are places that have higher cooling degree days. Precipitation. This is kind of an interesting graph to me. Median annual precipitation, the west, no surprise, is drier than the east. But you sort of see this interesting band move west to east, where the west typically tends to be the driest, and then you get into the Midwest, it's a little bit moister, and then you get into the east, and it's quite wet. There are obviously pockets in the Pacific Northwest that are wetter, and that makes sense, but you see these sort of bands of precipitation coverage in our model. Wind speeds on the right, north central plains, eastern Montana, Wyoming, Kansas. These are places that you'd expect to see high wind speeds, and we found those when we collected the data. And finally, the last two I believe I have here are, this is customers per line mile. So this is a measure of population density of the utility. And then on the right is lightning strikes. So on the left, not surprisingly, the upper sort of New England, the northeastern corridor, the New York, the Connecticut, the Massachusetts have high population density. There are some places in Las Vegas and in central Texas and in the Pacific Northwest that actually have, these systems have quite dense population. And that's something we learned here in this study. Lightning strikes, no surprise, Louisiana and Texas and sort of the Great Plains have the most strikes per customer. We wanted to normalize things by either customer or by line mile. Oh, I have one more actually. Electricity sales by customer. It turns out that Wyoming was a big surprise. They have a lot of sales per customer. Part of it is they don't have many customers. So the denominator is quite small, which makes the sales per customer quite high. But you see the breakdown here. And then transmission and distribution spending per customer, again, and this is related to the sales, it's really related to the number of customers and the sales. Wyoming, Idaho, these are places that spend a lot per customer, and that's presumably because they have long expanses of line and not very many customers. So there's a lot of maintenance going on for a few number of customers. All right, so I'm going to talk a little bit about the analysis method. We did some data transformations on the raw data that I discussed a little bit earlier. One of the ideas was that you can't just look at absolute weather. You can't just say, what's the rainfall in 2006 and what's the rainfall in 2007. Utilities are threatened through reliability impacts by abnormal weather. And so what we did is we transformed some of the weather metrics to capture what we call abnormal weather. We also included some nonlinear weather. I'm not going to get into that too much. And one of the ideas we had here was previous year expenditures would impact the current year reliability. So we lagged the expenditures data to be able to capture the fact that some of these impacts on reliability may not show up for several months after some spending has occurred. We followed a modeling approach from my colleague Ben Hohen, who studied basically how residential property values were impacted by solar and solar photovoltaic and wind systems. And so Ben has written a seminal paper on that subject, and one of the great things he did in this paper was he followed a sequential modeling approach, which I'll talk about in a second. And I'm going to spend very little time on this. It's just for the people that took econometrics or who are interested in statistics, the form is that reliability is on the left-hand side, whether it's SAIDI or SAIFI, and on the right-hand side, so everything right of the equals, is all of the observed or unobserved factors. And so the observed are the lightning strikes, the spending. There are other things going on which we either don't have access to or don't have the ability to measure. And so it's what's called a semi-log functional form. And this looks a lot more complicated than it actually is, but it's important to mention. So what we did is we take, on the top, as I mentioned, we transform the weather variables to come up with an abnormal measure of weather. And all we did, and the math looks a lot more complicated than it is, we calculated, for example, the average precipitation level for every utility over that 12-year span and compared each year to that average. And if it was above, we coded it one way, and if it was below, we coded it another. And the idea is that that's what we're testing. We're testing the deviations from the 12-year average. We did that with most of the weather variables. We also incorporated transmission O&M costs and distribution-related O&M costs. These are operations and maintenance costs. Divided them by the number of customers, and then we, inflated these values using what's called the Handy-Whitman index. It's an index that tracks how the costs of energy infrastructure have evolved over time. So we're putting them in constant year dollars. That's enough of the math. So of the equations. I'll talk a little bit more about math, but not too much. So there's sort of 4 steps we follow. We do what's called an F-test, where we want to see, are there really utility by utility differences between these models? And it turns out, yes. The F-test says, of course, all the utilities, there's some sort of difference across the utilities. So then the next thing we do is we look at this idea of random effects, and I'm not going to get into this here, but we test for random effects. And then what we did is, and this is really based on the Ben Hohen paper, we start with our old model, or as close as we can get to it, what we call the Edo et al. Model. In our model, it's called Model A. And we add groupings of what we're calling regressors, or factors that affect reliability. And we only add groupings that are related to each other. And as we add a different grouping, so we might add the precipitation variables as a group. And then we look and we see, how did the model do? Was it better fit? The idea of parsimony is we want to be frugal. We don't want to keep adding variables, because in econometrics, the more variables you add, you'll always get a better fit. Well, we don't want to do that. We want to pick the most, what we call, frugal model. And finally, we look, as we add these groupings of regressors, does the sign or the coefficient on all the regressors change, or some of the regressors change? That tells us that something's going on. There's some instability in the model. Based on all those criteria, we selected a base model, and then we interpreted the results, and that's what I'm going to show you here. This is a description of all of the factors that affect reliability in our model, and you see the Edo et al. Model, what was in that model. You've got basic electricity delivered, heating degree days and cooling degree days, and outage management systems, and then we have a year variable to try to capture that time trend, that 2% per year that we saw in the original paper. And then you've got these other 6 models, which is what's represented in this paper. It turns out that we ended up selecting F, Model F, the second one from the right. It had the best performance, hands down. And so all of the results I'm going to show are based on Model F. This is kind of interesting if you're into statistics. I'll just point out a couple of things here. These are just outputs. These are diagnostics from the regressions. One of the key graphics you want to look at is the one in the upper right of each panel. It looks like a normal distribution. What you want to see in a well-constructed model is a normal distribution here. This is basically a distribution of the error around the model line, the fit line. If you plot all of the errors, which points are above or below that fit model, you really want to see a normal distribution. In basically all cases, we're pretty close to normal, and so we're very pleased with how well this model performs. So here are the key findings, the takeaways. Are power interruptions becoming more frequent and lasting longer? If you include major events, and we saw this with the raw data, we're confirming it with the model, the total number of interrupted minutes or outages and the number of events are increasing. The key finding here is using Model F, the best performing model, we're showing that SAIDI is increasing almost 10% per year from 2000 to 2012 when you account for all of those factors. That's huge. If the major events are not included, the number of interruption minutes and the number of events are slightly increasing. The duration metric, SAIDI, is increasing 1.3% per year. This is when major events are not included. That's statistically significant. The trend for the number of events is increasing, but it's not statistically significant. I think it's marginally, it's very close to becoming statistically significant at the 10% level. It's just not there. It's very close. I think it's at 11%. So this is a graphic of all of the results, and some of the bars are shaded kind of a lighter color and some are a solid color. The solid color shading, whether it's blue or red, is a metric that's statistically significant. And it's highly statistically significant if it's got 3 asterisks after it. So as you can tell here, wind and windy squared, so this is where we have what we call a nonlinear term. Wind is clearly a driver of reliability. This should not be a surprise to anybody, but we confirmed it in this model. On the left-hand side, SAIDI without major events, here's the year variable. SAIDI is increasing 1.3% per year, and that's statistically significant. On the right-hand side, what we see is, this is interesting, as the share of underground line miles increases, you actually see a reduction in SAIDI, and it's significant. So as you increase the number of line miles underground, you see a reliability improvement. This is getting at power grid resilience right here. We show abnormally warm weather is correlated with lower duration. And then here's that year variable, and this is one of the major findings. One thing I want to point out, and this is a key takeaway from this work, is that we can say conclusively that severe weather or major events are leading to longer duration. If you look at the left graphic, what the year value is, 1.3%, and you look at the right, which included those major events, you see a dramatic jump in the duration. And you can basically interpret that as when you include major events, you see a significant jump in the time trend of reliability, the duration metric. So for SAIFI, same graph, this is the frequency metric. What we show on the left is that as you have more customers per line mile, so population density, and you're not including major events, you actually see a lower frequency of interruptions. And so what you could infer from that is that, potentially utility systems that are in more urban areas may have or may be correlated with less frequent outages. Again, windy shows up as a significant impact on SAIFI. It's correlated significantly with SAIFI. We also show for the first time that lightning strikes impact SAIFI when you consider major events. So here are some caveats to take away. We spend a lot of time talking about caveats in all of our presentations, but in our papers as well. One of the big ones that I talked about a little earlier is that there's inconsistent definitions of major events. We talked about that. There is an IEEE standard called 1366 out there for defining major events, but it's a statistical measure only. So it doesn't account for whether, a lineman backed into a pole and knocked the power line down, or you had a storm that actually, impacted the reliability that was beyond the control of the utility. So that's one of the challenges. IEEE 1366 is a step in the right direction, but it's purely a statistic way of measuring major events. The other issue is we were surprised to find that transmission and distribution spending wasn't statistically significant in this model. We expected it to be significant and have a negative coefficient, meaning the more you spend, the better your reliability is. But we didn't find that, or at least we didn't find that it was statistically significant. Well, what we think is happening here is that some utility investments in reliability are proactive and some are reactive. Some utilities, go and maintain lines before the failure occurs, and that costs money, and you see a resultant improvement in reliability. Some other utilities will spend money after an event has happened, which costs just as much, if not more money, but you see a decline in reliability because it was after the event. And so there's this issue of whether reactive or proactive spending washes itself out in the model and creates this lack of significance. That's something we're going to be exploring further. We didn't include capital investments. Part of the reason is we didn't have the data to be able to do that. Multicollinearity, this is a fancy term for meaning that all these weather variables are related to one another. And it's not necessarily a big problem in the model. It just makes the model error larger than it would be if we had like storms modeled perfectly within the model. Again, a lot of the regressors we use, like lightning strikes, are a proxy for major events. We're using lightning strikes as a proxy for severe weather. But we have other variables in there, like precipitation, that are also related to severe weather. So there are these issues of using these regressors and how they really relate to major events. And there are all these other unobservable, or what we call intangible factors, that we just either don't have the ability to get, or it's never been collected, or it couldn't be collected. One example of something that could be collected in the future, and it may not be over the whole panel time period from 2000 to 2012, but maybe in the latter period, is the penetration of smart grid technologies. So another example, teeing off what Seth just mentioned, they've released a paper today called Resilience for Free, is that these hybrid solar and storage systems, maybe these are new technologies that aren't being seen across the U.S., but 5, 6, 7 years from now, when you have more penetration of those types of technologies, those are things that could be included in a model like this. So the summary here is reliability is appearing to get worse over time, and it's really due to these major events, even though the major events are defined inconsistently. What we found is the total number of minutes that the average customer is without power is increasing 9 to 10% per year when you include major events, and about 1% per year when you don't. Wind speed is something that's consistently correlated with impacted reliability, but we found that there were no statistically significant results for transmission and distribution spending. So where are we going next? The paper hadn't even been out for a day before we started working on the next iteration. And so one of the things we're spending a lot of time on right now is really exploring this idea of reactive and proactive expenditures by utilities. I want to be very clear. Most utilities make both reactive and proactive expenditures, so it's kind of a little bit gray here, but we're really curious about how both capital and O&M spending is related to reliability, and we're just starting to get a handle on that issue. We also want to investigate whether investor-owned utilities and non-IOUs have statistically significant differences, and explore the relationship between reliability and the long-run deployment of other smart technologies. And finally, there may be more appropriate ways of modeling weather. And an example we heard from an engineer after he saw our study was, you should forget using abnormal wind. What you should include in your model is the number of days per year when the wind speed peaks above 30 miles an hour. And his thought was that these are the events, in his experience out in the field, these are the events that cause trees to come down on lines more frequently than just a simple average or abnormal weather. And so with that, I'm going to stop and hand the baton back to Seth for moderating questions. I will point out these two pictures on the bottom. The lower left, we're not exactly sure where this is. We're speculating this is somewhere in New York. It's an old distribution, what a distribution line looked like in an urban area, probably in the Northeast. On the right is a picture I took when I was in the UK last summer on vacation. And the interesting thing is that in some respects, the distribution system between the picture on the left and the right isn't all that different. And so with that, I'll hand it back over to Seth. Thanks for giving me the opportunity today.
Thanks, Pete. That was very interesting. Maybe the resilience-free is correct if this is how our distribution system is progressing or not progressing. Resilience may not be something that we're seeing a lot in a lot of these systems right now. So that was a great presentation. We had some very good questions come in. We had a few come in the beginning that were more related to Clean Energy Group. I'm going to save those. If we have time, I'll address those later, but I'd like to focus on ones more directly applicable to your work. So you're talking about the next step, talking about where utilities invest their money. The question we had come in was talking about a factor in outages being where they occur, on the transmission system or the distribution system. Curious if you looked into the difference between where the outages occur. And then a follow-up to that, the questioner wanted to know if you've gotten to the point where you can tell where utilities are spending their money on capital, and whether preventive maintenance such as vegetation management are where some of the money is going, and what are the financial incentives for, say, larger capital expenditures versus more maintenance as far as vegetation management?
Okay. So a lot of questions on sort of utility capital spending and where the outages are occurring. So this analysis is really focused on the distribution side. And in our experience, I've been told anecdotally, and I'd have to dig up where the source, the citation is here. I've been told anecdotally that 90% of the interruptions occur on the distribution side across the U.S. Again, don't quote me on that. Email me offline, and I can try to track down the official source for that. But what we're really interested in, distribution side outages, because that's where the majority of the interruptions are occurring. On the spending side, I think the second question on spending, one of the things we're doing here, just since this paper came out, is we're exploring what's called FERC Form 1. And FERC requires that investor-owned utilities submit a form called Form 1. And in that form, there are all these detailed lines about where utilities are spending their money, not only on capital improvements, but O&M. The problem with our study, what we found, collecting data for our study, was we were able to get O&M expenditures, annual operations and maintenance expenditures for investor-owned utilities, for co-ops and munis, through a number of sources, including the Rural Utility Service. But we weren't able to get the capital spending information for co-ops and munis because that hasn't been collected recently, or at least we can't find it. If somebody's found that, definitely email me. So we had to leave out capital investments from our spending metric. So to answer the question, you can find out where investor-owned utilities are spending their money using FERC Form 1 data. And if you're interested in learning more about this, and we're learning too, definitely email me and we can work through this together. We're just starting to peel away where the spending is occurring. Seth, was there one more question embedded in there?
I think there was just a question. If if you don't have a good handle on where the money is going, just the benefits of the big capital expenditures versus the O&M, the maintenance side. And were there differences in the reliability, the resilience benefit that you might see from those?
Yeah, like I said, we weren't able to include the capital expenditures either separately or with the O&M in our model. We only have it for investor-owned at this point, and we're just starting to explore whether capital expenditures and O&M expenditures have a different, impact on reliability relative to one another. I I'm going to go off, the rails here and speculate. My guess is it's probably a 50-50 balance, and you guys can hold me to that later when we actually get through the data. But I'm just going to say it's probably an equal mix of spending that impacts reliability.
Okay, great. Well, we'll hold you to that for the next webinar when you have those details out. So we had some rather technical questions come in as well. So was the outage data normalized? This person said that in their state, they had a study that showed SAIDI and SAIFI numbers were not comparable from utility to utility, even within the same utility over time. And they asked whether the 2% annual increase could actually be due to better data over time and not the actually increased outages.
That's a great question. So we didn't normalize SAIDI and SAIFI. We used SAIDI and SAIFI with and without major events as reported either by the PUCs or the utilities themselves. To the other point, we did do some tests, and I would encourage you to take a look at some of the results chapters and possibly the appendix of the report, which I believe is attached to this webinar. We did do some tests to explore whether the reliability was a function of potentially better or improved collection of SAIFI and SAIDI data over time. And so we started to explore this issue. Are we just seeing better data, or is there really a trend going on? And encourage folks to take a look at that. I'll spare the details so we can move on to other questions, but if you have follow-up questions, definitely email me and I can, point you to the right spot.
Great. And yes, the report is, if anyone looks at their dashboard on the side, there's a handout section that has a link to the report, and I think it's available online as well freely. So another question. Some of the non-weather causes that you showed in the pie charts, do you think those could be indirectly related to weather, such as trees and vegetation falling on power lines due to high winds? I mean, it seems like from your data that it was obviously the high winds that was one of the more significant findings of the report.
Definitely. That's the one thing to kind of take away, and I hinted at this with that multicollinearity reference, which is overly technical, but it's getting at this issue that all of these factors in some way or another are related to one another, and that doesn't bias the model at all. It just creates a larger error term. So yeah, vegetation and wind speed are, you could think of those as separate in that pie chart, but really they're interrelated to each other. So we're aware of that, and that's just a function of what happens when you have to model this kind of stuff. And so it's not a big issue. It doesn't bias the model. It's called multicollinearity. It just inflates the errors that if you could perfectly separate all of the factors independent of one another, then you wouldn't have any multicollinearity, and the error terms would be smaller.
Great. You may have addressed this with your slide that showed the normal distributions, but I'm going to ask anyways in case I am wrong on that. A person asked what the groups look like for SAIDI with major events. Was it a normal type distribution, binomial type clustering? They were curious if you were able to notice a difference that could be attributed to properties of the major event.
Yeah, Sam, I'm wondering if you can put it to slide 24 just to show that graphic again, if possible. To answer your question, the distribution of the error terms, whether it was SAIDI or SAIFI with or without major events, was here we go, up on the upper right-hand panel is the distribution of what we call the residuals or the error term. The line that overlays the bars of the histogram, that's a normal distribution. So as you can see, all of them are fairly close to normal, or very, very close to normal. The SAIFI without major events has the least perfect fit of the four, but it's still pretty close. So I hope that answers your question.
Great. There was a few questions came in different ways asking about the data that was used for the study. One person noticed that they didn't think that Phoenix or Tucson was included based on the maps that you had shown. So I'm just wondering, how comprehensive was the outage data that you had, and where did the data come from? And someone also wanted to know if there were a list of utility companies that were included in the report.
Okay, Sam, if you could go to slide 11, and then I'll do some color commentary here. We were able to get some level of reliability information from nearly 200 utilities. Not every utility reported all 4 of these metrics. So these are the unique number of utilities. One of these utilities may have reported just 1 of the 4. X number of utilities may have reported all 4, SAIDI with, SAIDI without, SAIFI with, SAIFI without. So when we map this, you see places, especially in Texas too. We heard this on a conference call a couple weeks ago. We're missing data for Texas. And what happens when you do this modeling is you have all of this SAIDI and SAIFI data, which is the primary, it's the left-hand side of that equation, and you have all these factors. The model will only, calculate results where we have all of these values lined up perfectly for every utility and year. So a lot of records end up getting thrown out during the actual modeling because we don't have complete data. It's called an unbalanced panel data set. So having said that, yeah, there are places where we did not have sales information, and there are places where we didn't have wind speeds for whatever reason. But, we had at least 100 plus utilities reporting all of, or some of the, at least one of the combinations of reliability metrics, if that makes sense. So, yeah, it's a work in progress. Next time maybe we'll have 250, and I'm hoping those additional 50 plus utilities will be co-ops and munis. As I mentioned, that's where we are underrepresented.
Yeah, and so the SAIDI and SAIFI data that you had, that's also the data that shows what outages the utilities incurred over that time, or did that come from a different source?
Yeah, so this SAIDI and SAIFI data came from public utility commissions, came from reliability reports filed by the utilities, came directly from utility press releases, and a whole slew of other sources. So it's a compilation of a number of sources. But I would say that the top 2 are PUCs and getting the information directly from the utilities themselves.
Okay, great, thanks. So here's a question. I know we're getting short on time. I think, Pete, you said you had a little extra time, so if that's okay with you, I'll get through a couple more questions here before we sign off. This relates directly to some of the work that we do here with Clean Energy Group. Someone wanted to know if customers using islanded energy storage systems, if the result of that would show up in the SAIDI and SAIFI data. In other words, could utilities directly affect their numbers by providing more resilient customer-sided systems like solar and storage?
That's a great question. I'm going to say that I don't think the data would be available on a national level at this point to be able to really explore that issue in our model. And that's one sort of level of answer. On another level, I don't have a good sense. I'd have to give it a little bit more thought, so I apologize, and we can talk offline about how customer-cited storage or whatever it is would impact these SAIDI and SAIFI values from sort of more of a theoretical level. So that's something I need to think a little bit more about. It comes down to how are the utilities measuring SAIDI and SAIFI, and whether these customer-cited storage facilities would impact the SAIDI and SAIFI numbers. I need to give that a little bit more thought, so I apologize for that answer.
No, it is an interesting question because just thinking about it, they wouldn't necessarily the utility wouldn't necessarily know that a building was still energized if it was disconnected from the system. So I'm curious about that, and definitely let me know if you come up with any answer on that.
And again, I think that it's correlated to whether there's smart grid infrastructure in place to let the utility know it's been disconnected too. So there are all these really interesting nuances here. Yeah.
So I'm going to just have one more question here because this relates to Hurricane or Superstorm Sandy, which is what the series is here. Post Sandy, many utilities spent significant dollars on tree pruning, vegetation management, and other efforts to make the grid more resilient and more resistant to storms. Is there any plan to collect and review post-Sandy data to see if there's any correlation there between the resiliency of the systems?
Great question. I have colleagues at LBL who are starting to explore these extreme events a little bit more closely. And don't quote me here, but I think one of the ideas is they're going to be exploring case studies in how these extreme events impact power systems. I'll tell you that I'm doing my own work in kind of a separate parallel research effort where I've built a model to estimate the costs and benefits of undergrounding power infrastructure. And so maybe on a future webinar, if you'd like to have me back, I could report on that model. I'm really interested in, applying it to some case studies to see whether, the benefits exceed the costs of actually undergrounding, because we know a lot of places in the eastern seaboard have been undergrounding after Sandy.
Yeah. All right, great. So stay tuned for the next webinar. Be looking forward to anything coming out of LBL about that. And thank you so much for joining us today, Pete. I think that we're going to wrap it up with that. If you have any further questions, please reach out to myself, Seth Mullendor, or to Pete, and you can contact us if you don't have his information there. This webinar will send out a notification to everyone when it's available online. Sam, you have anything else to note?
Well, we do have a few other webinars coming up this month, and you can find info about all of that on our website, resilientpower.org.